Hello, welcome back. The title of this lesson is called Inverse Functions. This is part one of several. So here's a concept that gives a lot of students a lot of problems, and even when you think you understand it, there are usually a few little aspects that you really ever either didn't think about or really just didn't understand to begin with. What I want to do is make sure you understand by the end of this lesson what an inverse function is, what the graph of an inverse function really looks like, but mostly just intuitively to know what an inverse is and why it's important in math. All right, so let me let you take a trip down memory lane with me just for a second. We know that we understand how to solve equations. Generally, in order to solve an equation for x, we have to kind of undo everything that's happening to x to put x by itself on one side of the equal sign. If something is added to one side, then we have to go ahead and subtract to get x by itself. If something is multiplied by x, then we usually divide. We do the opposite. Up until now, we've been saying that we've been doing the opposite to undo the operations to get x by itself. Really, we're going to dive a little bit more into that, and we're going to talk about the idea that you've already been kind of using inverses up until now. The additive inverse you've been using, that's what we call to undo addition. And the multiplicative or the multiplying inverse, that's what we do to undo multiplication. So we've already been doing that. But now we're putting different words. We're calling them inverses, right? But then we're going to extend that concept to functions. Functions can have inverses also. And that's where the wheels come off the train a little bit for a lot of students, because they can kind of understand what it is, but they have no idea why we're doing it. The reason that we're doing it is because later down the road, when we solve more complicated equations, in order to get x by itself when we're solving equations, we're going to do the opposite, do the undo operation. In other words, we'll apply the inverse function in order to get x by itself to solve more complicated equations. Right now, you've been doing inverses a lot. You've been subtracting or multiplying or dividing, whatever. But later down the road, especially with the exponential functions, we're going to have to do an inverse function to get x by itself. And so now we have to learn what an inverse is, and then we're going to apply that as we start to learn what the inverse of the exponential function is. And by the way, it's called a logarithm. So we're going to talk about logarithms. So this is very important to understand what a logarithm is. So first, let's go down and make sure you understand what some of these other things are. So we have the concept of the additive inverse. And believe me, I know a lot of people probably want to skip through this because they know what addition is, but just trust me, go through it with me, because the conclusions I'm going to draw about additive inverse is directly related to what an inverse function is. So it's very important that you follow me through this. So let's say you start with a number, any number you want. I'm going to pick a number, 14. That seems like a nice number. All right, and I'm going to add something to it. So I'm going to change this number. I'm going to add, let's change colors. I'm going to add something to 14 and change that number. I'm going to add 5 to it. So now if I were to add that together, that would be 19. But let's say I want to undo this. I want to change it back into 14. Well, I have to do the opposite of the addition that I did here, which would be subtraction of the same number 5. And what I would get out as a result of that would be 14, exactly what I started with. Okay? You might say, this is pretty simple and pretty dumb. Why is he teaching me this? What I'm trying to say here is the additive inverse of the number 5 is the number -5. Now you see that symmetry of the number line, the positive numbers and the negative numbers. The negative numbers are the additive inverses of the positive numbers. You probably saw this definition way back in Algebra 1, but you don't care back then because who cares? They're additive inverse, great. What you've done here is you take a number, you change it by adding something to it. You have to do the inverse to undo that to get back what you started with. I want you to remember this concept of getting back what you started with, because this concept of getting back what you started with is exactly how we're going to tackle inverse functions here in just a second. All right? So as another example, let's say you start with 20, the number 20. I'm just making this number up. And let's say you subtract 6 from 20, but then you want to undo that. How do you undo that? Well, you have to add 6 back. What do you get back as a result? 20. You start with something, you do something to it, you immediately undo it, and you get back exactly what you started with, right? And so you can say here that the additive inverse of -6 is +6. Okay, so we talked about additive inverses. Awesome. How do we apply that? Well, let's talk about something related to that. Let's talk about the multiplicative inverse. It's a really similar concept. It's not any harder at all. All right, let's pick a number out of thin air. It can be any number I want. Let's pick 16. And let's say I multiply 16 by something. Let's say I multiply it by 4. But I want to get back 16. So how do I undo this multiplication? I can't add or subtract the negative 4. That's not going to undo that because this is multiplication. How do I get the 16 back? Well, I'm going to have to multiply by 1/4, right? And that's going to give me 16. So you see, by multiplying by 4, I've changed the original number. But I can immediately undo that by multiplying by the inverse of 4, but not the additive inverse, it's the multiplicative inverse. So what it's telling you is that the inverse of multiplication is division because you're multiplying something, but what you're multiplying by is division. So the inverse of multiplication is division. The inverse of addition is subtraction. It's exactly what I said in words at the very beginning of this lesson. The goal is if you start with something, you multiply by something, you multiply by the inverse. To undo that, you get back what you started with. We get back what we started with. We get back what we started with. That's what I want you to remember all throughout this lesson because inverse functions are all about how to get back what you started with. So we say that this multiplicative inverse, 1/4, we say that it undoes. It undoes. That's not a technical word. That's my word. It undoes the multiplication by the 4. So they kind of annihilate each other and you end up with what you basically started with. So now we're going to move the train along a little bit and talk about inverse functions. Because that's where, again, students start to they have no idea why we're doing this or anything. But basically what happens is an inverse function is when we want to kind of undo what the first function does. It's like the opposite function. Think of peanut butter and jelly, or mayonnaise and mustard, or ketchup and mustard, whatever. You have these little pairs of things that go together. Every function, I shouldn't say every function that we'll talk about how to figure out if a function has its inverse, but most functions have a cousin function called an inverse function that essentially undoes what the original function is doing. And so mathematically, that means it's going to literally take and undo the mathematical machinery of that first function with the inverse function mechanic. So let's take a concrete example. All right, let's see how much space I have. I don't want to save some room. Let's say I have a function, f of x, and it's equal to x plus 4 over 2. This is a really simple function. And let's say I have another function, g of x, and it's equal to 2x minus 4. Now I'm going to give you the punchline. These are inverse functions of one another. You cannot tell by looking at them that they're inverse, so just forget it. Especially if I give you a more complex function, you'll never be able to look at it and just say, oh yeah, those are inverse functions. No, you're never going to be able to do that. I'll show you how to be able to tell if they're inverse functions. But I'll tell you ahead of time, these are inverse functions, so they're special. They go together, right? They're very, they have a lot of synergy between them, you could say, right? Let's take a look at what that might look like, or what that synergy is. Let's take and look at the following thing. Let's look at g of 1. This is the function g. Let's put the number 1 into there. What would we get? We'll put the number 1 into there. This is the input, right? We put the input into here. What do we get? 2 times 1 minus 4. That's what we get. So then when we calculate that, we're going to get 2, then minus 4, we'll get negative 2. So g of 1 is equal to negative 2. Now, just like we learned in the last section with composite functions, you can chain these functions together or nest them, however you want to think about it. We talked about composite functions in the last lesson. If you haven't done that, you have to know that to get this. So let's take the output of this function here, and let's run it through the other function, which you know ahead of time, it's an inverse function. So let's see what happens. Take this guy, and let's run it through the f function, which is the cousin function of that guy. And what we get is f of g of 1, which means we've done this. So then we say, let's run the number negative 2 in through the f function, because that's what we got as an output. We stick it into the outermost function here. Okay, what do we get? Take this over here. What we're going to get is, where do I want to do it? Let's do it right here. It's going to be negative 2 plus 4 over 2. Just take it and stick it into here. What do we get here? Negative 2 plus 4 is going to be 2 over 2. So what we get is 1. So f of g of 1 is equal to 1. I want to make sure you understand what's happened here, and in fact, it's not so obvious at first. But look back to what we did in the beginning. I said additive inverse. We start with some number, we add something to it, but we do the inverse and we get back what we started. We start with a number, we subtract something, we do the inverse, we get the number back. The inverse gives you back what you started with. It undoes the thing that you've done to it. So here we multiply by 4, we do the inverse, and we get back what we started. Here, we know that these are inverse functions because I'm telling you they are. If you put the number 1 in here, we get this out. But if we take and run that through the other function, we get the number 1 out. We put a 1 in, and we get a 1 out. That's exactly what we did there. We start with a number, we do something, we do the inverse, and we get what we started with. We start with a number, we do a function, we do its inverse, and we get the number out. Inverse functions undo each other. I'll say it again. Inverse functions undo each other. I'll say it a third time. An inverse function undoes what the other function does. That's what they are. They're special functions. These are not random functions off, just randomly taken. They're specially crafted to be inverses of one another, right? So let's spell this out a little bit more, okay? I'll say note. What did we do here? G of 1, that's what we started with. We calculated that. We got an answer of -2. But then we ran that function through, or the answer, through the other inverse function, which is f, and we got an answer of 1 out. We started the chain by putting a 1 in. We went through this calculation intermediate value, then running it through the inverse, and we get a number out that's exactly equal to what we started with. So these are the same. These are the same. Now, I want to go off to the side here and show you something. We did f of g of 1. Now, let's go over here to the side and let's calculate something similar. Instead of f of g of 1, let's calculate g of f of 1. So this is a composite function. We got a 1. We're going to do the composite function again, but we're going to flip it around. And if you remember, I told you in the last lesson when we did composite functions, I said, in general, when you flip the order of the composite function, you do not get the same thing. But there's a big exception, and the big exception are inverse functions. Inverse functions always undo each other no matter what order you do them. That's why they're special. So here we did f of g of 1. Here let's do g of f of 1. So how do we do that? Well, we say, well, f of 1 is this. It's going to be 1 plus 4 over 2, which is 5/2. It's an ugly fraction. But let's take that ugly fraction and we're going to put it into here. So g of f of 1 means that what we do had a 5/2 here, so we do g of 5/2. Because that's what we calculated. We're feeding that into the g function. What is the g function? It's this. It's 2 times the input here, which is 5/2, minus 4. So I've taken this and I'm sticking it into the g function. But notice the 2's cancel. So what you get is g of f of 1 is the 2's cancel, so you have just a 5 left over minus 4. So g of f of 1 is just equal to 1. And notice what happens is that this is the same thing. All right? That's one of the major conclusions I want you to remember from this. I told you in great detail in the last lesson. When you flip the order of the composite function, you're not going to get the same thing, but that's for random functions. I'll pull a random function. F of x is x squared. Pull another random function. F of x is 2x minus 3. Okay, those are random. If I do the composite functions in both orders, in the different orders, I'm going to get different answers. But inverse functions are special. They always undo each other. I put the input in of a 1. I run it through one of the functions, then I immediately run it through the inverse function, then I get the same exact number out. I stick a number in here, I run it through the g function, I run it through its inverse, which is the f function, I get exactly the same number out, which is 1. All right? And that's going to be the case of all inverse function pairs. All right, so let me make sure I haven't missed anything so far. They undo each other, g and f undo each other, and you're always going to get that input function back, that input number back out. So what I want to do now is I want to give you a few more examples of this whole undoing business. And then after that, I want to graph the inverse function. So let's rewrite these functions here just to have them handy. F of x is x plus 4 over 2. G of x, 2x minus 4. Same functions. I haven't changed anything. I just want to have everything down low here. Now let's do the same thing. Let's say f of -3. Let's put a -3 in here. So it'll be -3 plus 4 over 2. So we add them on the top and we get a 1, and we get a 1/2 out of that. So what we figured out is f of -3, this intermediate answer is 1/2 after we run it through one of the functions. Let's take that and then run it through the other function. So you'll say that g of f of -3 is going to be g of 1/2 is going to be equal to, I have to put a 1/2 in here, 2 times 1/2 for x minus 4. The 2's are going to cancel. So what I'm going to have here is just, the 2's are going to cancel, so we're going to have a 1 minus 4, which is 3. Notice the 3 is exactly what I'm sorry, not a 3, -3. 1 minus 4 is -3. It's exactly what I started with. That's exactly my input here. So g of f of -3 is, surprise, -3. Because these are inverse functions, whatever number I put in, I run it through one of the functions, and I run it through the other function, and then I get exactly what I started with. It's exactly like undoing each other from before. So just to spell it out one more time, I could say, let's see here, f of -3 yields a value of 1/2, but then I put that through the other function, g of 1/2, and that yields a function of, sorry here, yeah, g of 1/2 yields a number of -3. So I start the chain by putting a value of -3 in, and I get out of the chain, or out of the nest, however you want to look at it, the same exact input value. They've undone each other. And it turns out that this undoing of one another is going to help us solve lots of equations down the way that we don't know how to solve now. Mostly in the beginning we'll be solving exponential equations because the exponential function has an inverse. I'm going to talk about it later. It's called the logarithm. So if you take the logarithm of both sides of the equation, you kind of undo the exponential function, and then bam, the variable drops out because you've kind of annihilated and eliminated the exponential part because you've done its inverse. You've undone it. Just like we add in order to undo subtraction, and we divide to undo division, we do the inverse, which might be taking the logarithm, to undo the exponential function. Here we don't have any exponentials. I'm just explaining what these things are, what these inverse functions are. All right? So then let's do one more just to bring it home. Here we have said with these two functions, we put a number in of 1, run it through both of these functions, and we get a number 1 out. We reverse the order of the functions, doesn't matter. We still stick a number 1 in, we get a number 1 out. Let's change the input. We put a number -3 in, we run it through both functions, we get a -3 out. Now, let's not put a number in, let's just put a variable in. Let me rewrite the functions. F of x is equal to x plus 4 over 2, and g of x is 2x minus 4. Same functions. Now instead of putting a number in, calculating it, and putting it to another and calculating it, let's just do this. Let's calculate generally f of g of x. In other words, we're not putting a number in, we're leaving the input of that innermost function just a variable. We're letting the input to the whole process be any number we want, we just call it x. So when we put x into g of x, what do we get? We get this. And we have to take this thing and put it into the f location. So that means we have to take this whole thing and stick it where x is. So it'll be 2x minus 4 plus 4 over 2. We just took g of x, whatever it was, and we stick it in the x location right there. Now look at what you have. You can drop the parentheses now. 2x minus 4 plus 4 over 2. This is going to go to 0. So you're going to have 2x over 2, which is going to give you, once you cancel x, notice what's happened. We stick a value of x in, which means any value I want, I run it through both functions, and I get the same exact value back. That's exactly what was happening over there. Put a 1 in, get a 1 out. Put a -3 in, get a -3 out. Put any value I want in for x, I still get exactly the same value of x out. That's what that's telling you. When you operate an inverse on the inverse function on the other function, they annihilate each other, and you're just left with whatever input you had to the whole chain. All right? Now, just to make sure we're on the same page, let's run that same process through in reverse. Instead of f of g of x, let's do g of f of x. Again, leaving it general, we have f of x. We're going to put it inside of g. We have to stick this whole thing and put it in there. So it'll be 2 times x, but this x is the entire function, x plus 4 over 2. And then we have to do this guy. Now, when we have a 2 on the outside and a 1/2 here, they can cancel like this. And so what you're going to have is x plus 4 left over. That's all that's left out of this, but then you have a minus 4. And look here, this goes to 0, so you get an x out. So you stick an x in, you run it through both functions in reverse order from before, and we still get exactly the same thing. So what we have concluded is that f of g of x is equal to x, and we've concluded that g of f of x is equal to x. Now I could have started this whole lesson by giving you this gibberish here and said, hey, there are these things called inverse functions. F of g of x is x, and g of f of x is x. Don't you understand? Nobody's going to understand that. I don't even understand that when I say it out loud. It doesn't make any sense. But by going through the whole thing, I hope you can understand what this means. This is what you would typically see in most textbooks as the definition of the inverse function. And that definition goes like this. F and g are inverse functions if the following thing, if this is true, right? So this is what I'm going to circle as the definition of the inverse function. So somewhere in your algebra book or pre-calculus book or calculus book or whatever, they're going to define this thing called an inverse function. They're going to say f and g are inverse functions if f of g of x is x and g of f of x is x. And then probably have some other words about the domain. You have to make sure the domain, that this is true on the domain of g and that this is true of the domain of f. But assuming both of these are smooth, continuous functions with no, asymptotes, infinities, or anything, they're very well-behaved functions, then this is going to be true for all x, right? For all input values of x. Whatever input you put in, you're going to get an input, you're going to get exactly the same number coming out of the other end. Once you run them through both of these functions, it won't matter the order in which you do it. This is the definition of an inverse function that you're going to see in most books. But we just went through the process here so that you can hopefully understand it a little bit more. All right, now what I want to do is just as important as everything we've done up to this point, we want to graph these functions. I want to show you what a graph of a function looks like right next to what the graph of its inverse looks like, because it turns out there's a really easy way to visualize what an inverse function will look like, and it helps us understand what they're really doing, all right, what an inverse function is really doing. So what we want to do is we want to plot both of these functions. All right, so we have these two functions here. We have f of x is equal to x plus 4 over 2. That was function number 1. And g of x is 2x minus 4. This is a line, and this, you might not realize it, but it's also a line. Let's kind of manipulate this a little bit. F of x, this can be broken up as x over 2 plus 4 over 2. Just divide each term by 2. Of course, this is going to be f of x 1/2 times x plus 2. mx plus b. mx plus b. They're different lines. The y-intercepts are different, and the slopes are different, but they're both lines. So you can immediately tell that they're both going to do something, but they're not going to have any squigglies, and they're not going to have any parabolas. They're not going to have anything crazy like an ellipse or a circle or anything like that. They're both going to look like lines. So what I want to do is I want to graph this f function. I want to graph this right on the same graph as this guy. So it's probably going to take a little bit of time, but I really encourage you to hang on with me because it's really important for us to get there. It's very important for us to actually to do this together. So what I want to do is, first of all, write the functions down again. All right. The first function, let me go and write them up in the upper left-hand corner here. The first function, f of x, was 1/2 x plus 2. That's what we just wrote down. And the other function, g of x, is 2x minus 4, like this. So those are the two functions we want to graph. Fortunately, they're really easy to graph because they're just lines. So what do I want to use to graph these guys? What color? Let's try this one. That's probably not going to look so great. Let's try, we'll try this one. Okay, the first one. All right, we have, for the first one, a y-intercept of 2. So here's 1, here's 2. So I'm going to put a dot right here. It passes through this point. But the slope on this one is 1/2 x. So that means I rise 1 and I run 2, okay? I rise 1 or 1, 2. There's different ways in which you can do it, but let's go ahead and do it that way. Up 1 over 1, 2, because this scale is 1 tick mark and this scale is 1 tick mark. So up and then over 2 like this. And then I can go, I can do the same thing here. I can go down 1 and over 2 like this. Something like this, okay? Because it's going to be up 1 over 2, up 1 over 2, something like that. So I can draw a line smoothly through those points. So let's do that real quick and see if I can not drop my paper in the process here. Try to do the best I can. It's not going to be perfect, but let's try to get it as close as we can, because there actually is something really neat that I want you to be able to see. So it's going to look something like this. Like that. All right, let's just double check myself. Okay, so this function, f of x, is equal to the 1/2 x plus 2, but remember that just came from x plus 4 over 2. It was the same exact thing. So we'll say x plus 4 over 2. So this is the graph of this function. All right, then let's go ahead and graph the other one. And for that one, I think I want to try to use, let's use black. So 2x minus 4. So we have minus 4 means a y-intercept, -1, -2, -3, -4. It crosses right there and a slope of 2. That means up 2 over 1. Up 2 over 1, like this. Up 2 over 1, like this. So it goes through those 3 points. Let me see if I can graph it through there. Something like this. If I can get there. It's going to look something like this. Okay? Something like that. Not perfect, but you get the idea. Now, in your mind, I want you to extend this blue line. Of course, it goes on and on forever, and extend the black line. It goes on and on forever. Now, the interesting thing I want to show you is, well, let me go ahead and draw, I guess write this down. This is f of x is 2x minus 4. That's what that is. Now, don't they look interesting? It looks like they're a mirror image of one another. One of the functions, its inverse, is just the reflection of that function over a certain line. Can you spot what that line is? The reflection of one to the other is going to be through this diagonal line right here. So let me take this off and try to draw this line. So this is where the mirror would lie if we were going to actually flip this guy over here. So to get the inverse, all you do is you take the function graphically and you flip it over this red dotted line. And the red dotted line is a diagonal line, y is equal to x. It's straight down the middle. It's y is equal to x because the intercept is 0 and the slope here is 1. Rise 1, run 1, rise, run. So it's just a dotted line of a diagonal of 45 degrees, which means it goes right and it splits these guys in two. So graphically, you never do this graphically, but if I just said, hey, here's a function, right? It's a line. Graph its inverse. All you would do is somehow mentally map all of these points across a dotted line here and then draw your line, and that would be the inverse function. If the blue line were not an actual line, but some other function, because we're going to have inverses of all kinds of functions, all right, then the same thing will hold. If this thing had some kind of squiggle in it, then we could still reflect it over and we would have a different squiggly line, but it would be reflected over to the other side. That would be its inverse. Now, I want to talk about a couple of things. I want to mark a few really important points off of this graph, okay? Let's see, what is this point right here? This is -2, 1. This point right here is -2, 1. How can I read that? -2, 1. If I run it through this function right here, if I put -2 into here, then I'm going to get a -1. I'm going to add it here, I'm going to get a 1. So -2, 1. What other point is on this guy? Let's go to -3. And then what is this? This intersection right here. So this point is -3, 1/2. You can just read it right off the graph. Here's 1 and here's 1/2 there. If you put a -3 in here, and you do the math here, you're going to get a 1/2 out. All right? So these points are also on the inverse function over here, but the way it works is what happens is these points are going to be exactly flipped around. So let's go and take a look at that by switching to black. And let's say, what would this point be? The mirror image, in fact, you can see I already have it here. The mirror image when you reflect it over is this point. So -2, 1, this point becomes 1, -2. Look at that and stare at it. What you've done is the inverse maps every point on the function to another point that is kind of its mirror image cousin, but what happens is I take the coordinates and I flip them around. So -2, 1 becomes 1, -2. And let's look at this. If I take and literally go straight through this guy and down here, it's going to be this point right here, right? Which is -3, I'm sorry, not -3, it's going to be 1/2, -3. 1/2, -3. This is 1/2, and then -3. It's right there. So this point maps with this one, and this point maps with this one. Every point on this line is going to have a cousin partner point on the inverse line. And every point here is going to relate to every point here by simply taking the coordinates and flipping them backwards. Taking the coordinates and flipping them backwards. And that flipping backwards business of taking every point on the function and flipping them backwards to make the inverse, that is why the functions undo each other. Right? Because if you think about it, if this is the inverse, if this is the function and this is its inverse, then if I take any number in, let's say I put -2 as my input. I put -2 in, I get a 1 out. But then I take that output and I stick it into the other function, I put a 1 in, and what am I going to get? A -2 out. You can see I take the output of this, stick it in here, and I'm going to read off a -2 out. So I started with -2, I ran it through this function, I run the output into the other function, and then I get the same exact thing back. Started with -2, and I ended with -2. Right? Same thing here. If I stick as a starting point -3 in, I get a 1/2 out. If I take that answer and put a 1/2 into the other function, I get a -3 out. So you see, that's what we were doing all along here. I put a -3 in, put it through both of the functions, I get a -3 out. I get exactly what I started with. Put a 1 in, put it through both functions, I get a 1 out. Put a -3 in, run it through, take this point, run it through, I get exactly what I started with. Start with a -2, get the intermediate, run it through here, I get the -2 out. So graphically, I'm showing you why this undoing business works. It's because this thing is a mirror image reflection over 45 degrees, which basically means every point here has to be flipped around like this, which means every time I stick an input in here and get a number out, and then take that number here and get the corresponding number out, I'm going to get exactly what I started with. So the bottom line, punchline, most important thing I want you to get out of this, other than the math that we've done before, is if a function has an inverse, then that inverse will be that function reflected over a 45-degree line, y is equal to x. This is the inverse function of this, and the same thing goes true. If this is your input function, then its inverse will be the blue line. So it's not one way, they're inverses of each other. F is an inverse of G, and G is an inverse of F. And they're both mirror image reflections, obviously over that line 45 degrees, with the points flipping around, and that is why they undo each other. All right? So if you can, in your mind, envision this being more complicated than a line, and you could flip it over, you would still have the curve, but it would be rotated down, the same kind of thing would hold. All right? One more thing I want to talk about before we close, because I've already pretty much gotten everything out that I want to get out. But one important thing I want to say before I get into go off to the very final end is that not all functions have inverses. Most of them do, but not all of them. I want to tell you really quickly how you can tell if a function has an inverse, and we're going to practice it more in the next lesson. All right. For a function to have an inverse, it must pass what we call a horizontal line test, basically. So for f of x to have an inverse, it must pass the horizontal line test. I'm not going to write that out. Horizontal line test is very, very easy to understand. All right, let's take a look at this. First of all, let's look at what we have here. A horizontal line test means if you have a function and you start crossing a horizontal line through this function, it can only cross in one spot. Horizontal line only cuts this function in one location anywhere. So that means when I map it, then the inverse function will pass the vertical line test, because for a function to be a function, it has to pass the vertical line test. So if you're going to say this thing has an inverse function, you need to make sure it passes a horizontal line test so that when you flip it, it'll pass a vertical line test to be a function. So let's take a look at something that doesn't have an inverse, right, as an example. Let's say we have a graph here, and we have our nice friendly parabola. F of x is x squared. Does this function have an inverse over this whole domain like this? Well, all you have to do is say, well, does it pass a horizontal line test? Well, no. Fail the horizontal line test because it cuts into locations. If it cuts in more than one location, then it's not going to work. Now, what would happen if you actually tried to construct an inverse with this thing? Right? What would happen, remember, the inverse function would just be the mirror image reflection of this thing over that 45-degree line right here. So what would happen is the inverse function would be something like this, because if you remember, that 45-degree line is somewhere like this. So the original function was like this. You flip it over, the inverse would be something like this. But the inverse has to be a function. And remember, all functions have to pass the vertical line test. This thing fails the vertical line test because it cuts in more than one location. So the reason this thing doesn't have an inverse, the reason we have a horizontal line test is because once you mirror image reflect it, it has to pass a vertical line test. So if it fails a vertical line test, then it's going to fail a horizontal line test for the original function. So in most books, what you see is they'll tell you, if a function has an inverse, it has to pass a horizontal line test. All lines are going to pass, or except for horizontal lines, they're going to pass a horizontal line test, right? So all lines have an inverse. But this parabola over this entire domain like this does not have an inverse. So that's what you would write down on your test. But other functions that we could draw will have an inverse. And in the next lesson, we're going to get a little bit more practice with that. So we have learned a lot in this lesson. It's a really important topic because inverse functions feed into so many of the more advanced kind of lessons in the curriculum, whatever your class you're studying, pre-calculus, calculus, or algebra, inverse functions feed into that. We talked about an additive inverse. All we're doing is when we add something, we have an inverse to undo it. We get the same number back. We get the same number back with multiplication by essentially multiplying by a fraction or division to get the same number back. And then we said functions can have inverses also. These are inverse functions. Now we know why with their graphs, because they're a reflection across the 45-degree line like that. But basically, whatever number we put into this thing, we're going to get it back once we run it through both of the functions. And we prove that is true by relaxing the numbers and just letting the input be a variable. You run it through, you get the same number out that you put in. You flip the order, you run it through, you get the same number out that you put it in. So inverse functions are inverses if you run it through both of the functions and get the same thing out, no matter the order in which you execute that guy. Then we plotted both of those functions and showed that the line, in this case of the function, has an inverse by reflecting it over a 45-degree line like this. And we said that every point on the original function has a corresponding point on the inverse function where the coordinates are flipped around. And the reason the inverse functions undo each other is because of those coordinates flipping around. So if I stick a number into the original function, I get an intermediate number out. I take that number into the other function and I get the same number out that I stuck in to begin with. And that will happen for any number that you put into this inverse function pair. It's a lot of material. But make sure you understand this concept, because in the next lesson we're going to be calculating the inverse function, figuring out what the inverse, I just told you these are inverse functions. I didn't tell you how to figure it out. I just said here they are. In the next lesson, we're going to actually calculate what the inverse function is and sketch them and figure out if it passes the horizontal line test and all of that stuff. So make sure you understand this. Follow me on to the next lesson. We'll continue working with inverse functions in algebra, pre-calculus, and calculus.